Jetzt ist aber, sind alle im Zuhörmodus.
Ja, will, dass ich aufnehme. Ich kann, aber ich will gar nicht aufnehmen. Was ist das Problem jetzt?
Jetzt hast du es angeschaltet, jetzt sehen uns alle, ne? Nicht so gut.
Wollen wir wieder ausmachen?
Geht nicht. Richte es einfach ein und dann ist gut. Das war ja jetzt.
Da kam ein Bildschirm, genau, es war das Teilen, dachte ich. Macht nichts.
Naja, es sind
Genau.
3 Leute drin. Das ist nicht so schlimm.
Hallo, greetings. So. Everything all right. So, now you should also see me.
Ist doch okay, dann machen wir jetzt die 5 Minuten noch. Also dein Desktop, mach mal dein PowerPoint an.
I would start now. Hello and welcome. Hello and welcome to our webinar. My name is Lukas Gerlich, and together with my colleague Konrad Seidel, we will present you the material development for MRAM and FRAM material development. We are working at the Fraunhofer IPMS, and we show you our activities in the memory region and what we can offer in the framework of the SN+ project. At first, I would start with introduction of Fraunhofer IPMS, business unit CNT. Then we switch it a little bit. So Konrad will start with a ferroelectrogram material development. And afterwards, I will come to the MRAM material challenges and its characterization. Afterwards, some slides about the SN+ showroom offerings. And yes, here we are working on the chip level. And in our case, the memory is mostly embedded in the interconnects, as you can see here. So the Fraunhofer Society is known for applied research on benefit of society. So it's for the industry as a service and for the public. This is the European innovation powerhouse. So we have more than 70 institutes in Germany with more than 26,000 employees and more than 2.6 billion turnover euro. Then we drive ideas to market. So here from sketch to products, or like in our case, from lab to fab. The Fraunhofer Institute of Photonic Microsystems, the headquarters is located in the heart of Saxony, the so-called Silicon Saxony, which is the largest microelectronic network in Europe. There are more than 2,000 semiconductor companies and more than 60,000 employees dedicated in the semiconductor area. So it's a combined clean rooms area of more than 52,000 square meter and quite high turnover. So we are part of a Forschungsfabrik Mikroelektronik. It's a cluster in Germany with more than 2,000 employees in 13 institutes, also dedicated for the semiconductor area. And of course, we are also in a lot of networks like SEMI, Photonics, or SPI. So where we are in Dresden? In Dresden, we are located in the north, where Fraunhofer IPMS, the business unit CNT for 300mm, is directly between 2 big 300mm fabs, which one from Global Foundries, Fab 1, and from the new fab from Bosch, just established in the last years. And we are less than 7 kilometers away from Infineon Technologies, which has 300 and 200mm production. And the other 300mm wafer institution here in Dresden is the ICDM Asset, who is focusing on packaging technologies. So we at Fraunhofer IPMS have a fully industry standard CMOS clean room with 4,000 square meter of area. we have more than 80 tools for 300-meter inline processing and metrology, and lab tools for this. We are here located in Dresden, besides a lot of fabs, and we just moved from Infineon side and finished the movement this summer. Before, Infineon was our landlord. Now we have our own clean room with own infrastructure and own facilitation, and we were happy to start this in autumn. And with these words, I would like to give over to Konrad with his memory topic. Thank you.
Lukas, thank you so much. Yeah, now you should see my screen. Lukas, just a short confirmation, please.
Yes.
Thanks. Okay, then also good afternoon from my side. Hello, welcome. Yeah, so first of all, I'd like to introduce the motivation why we'd like to advance in the memory area, also doing material development. And yeah, if you look around, the world is full of memories, and yeah, even in hidden places like a dustbin, you will find an ID tag which is storing your individual location ID of the dustbin, and so for that you need a memory, and of course all the other applications which are commonly known. On the other side, there are a lot of memory solutions, and it's quite confusing, of course, which one is matching to which solution. And yeah, and the message is, of course, not every memory is fitting to a certain application. We have to tailor it and with respect to application needs. And there are a lot of factors influencing the decision. So, of course, speed, latency, storage capacity are very strong factors, but also more and more, and not even more and more, also beyond that, there are a lot of other factors which are influencing the decision of a memory, of the which memory to take out of the shelf for a certain application. And yeah, there is not the only single memory concept which could match all the application needs. First of all, let's focus on speed, latency, and storage size. So yeah, this leads me to the very famous memory hierarchy, and this is a kind of classical view on the memory. So you have looking towards the CPU cores, very fast memories, which are from the concept and classical concept point of view non-volatile, volatile, and below that there are larger storages with larger capacity, which are then also non-volatile, but with the lack of speed. So and also meaning that you always sacrifice something if you want to optimize the memories. Yeah, so that's the classical view. And of course, there are also in the recent years and decades also stronger needs developing towards low power solutions, small size memory solutions, especially when implementing it in low power sensor nodes. And for that, we have to make this area also non-volatile, meaning that the classical hierarchy is now more and more impacted also by non-volatile capabilities, which allows us to be much faster in processing. Also, you don't need to fetch memory content from a larger storage somewhere in the background. You have it directly in your system, in your CPU, without even if you switch off the power. And for that game, especially, you need to establish memory concepts which are non-volatile and also fast at the same time. And there are several memory concepts in discussion. Here's especially they are called emergent memories. I mapped it together with also the classical ones like NAND flash, SRAM, and so on. But you can see it's not very precise. There are a lot of publications around with different, of course, speed performances in terms of write time, but maybe inappropriate. It's the right region. you can see that there are several emerging memory concepts which are very promising for that area and also to compete with or get close to SRAM, DRAM concepts. And yeah, in our talk, so Lukas and mine, we will focus on MRAM and FRAM today. And first of all, we'd like to start with the FRAM, and I will show you on the next slides some aspects in the development of FRAM and the motivation why this is also an emerging memory concept. So yeah, that's first of all, I'd like to introduce you that, also directing to the hafnium oxide-based ferroelectric materials, which are very potential for using in FRAM in FRAM memories, and for that also all the aspect with respect to material tuning and also future perspectives. Yeah, if you to introduce the FRAM, it is very worthy to look at the DRAM concept because it's quite similar. In the DRAM, you have a storage capacitor with an access device, and that is the same for the FRAM concept. The only difference you can see in the memory cell, instead of the capacitor, which is based on an charging, classical electrostatic charging effect, which is of course also underlying underlying leakage mechanisms, which requires regular refresh cycles and also very low retention time on the DRAM side. This is solved by implementing so-called ferroelectric material, which features remnant polarization and which helps to store the information also when switch off the power from the system. So that's the main difference. And also there are little differences in the implementation, so how you implement the counter contact to plate line or ground and so on. But both comprise a very high speed features, and the scaling of this material was so far a bit more problem. Yeah, also just to understand how we come to from a memory cell to an array, there are a large variety of architectures. This is just an example how it is implemented. So you arrange these single cells, either this or this one, in rows and columns, and so you can, by means of that matrix, you can achieve larger storage capacities in the megabit region or even higher. Okay, now I introduced the ferroelectric memory, FRAM. In the next pages, I just like to those who are not so familiar with ferroelectric materials, just give a very short introduction how the ferroelectric about the features of the ferroelectric materials. And yeah, so what is the special thing is that the ferroelectric material is contains of a crystal structures with a polar axis, which allows, due to certain ion shifting, two stable states. And those states are also remnant. That means you can, by applying a positive bias, the so-called coercive field, you can switch the states, and by an opposite field, you can switch it back to the other state. And just by evaluating either the current when switching, of course, you get a kind of current peak in the positive and negative direction, or by evaluating the intrinsic field, you can differentiate the two states. Yeah, and that brings us also into the device implementation. Just another information. The word ferroelectric sounds like iron, but it is not iron. So it's really not containing any iron. It is just very similar from the behavior point of view, like ferromagnetic materials. Therefore, the ferroelectric materials are ferroelectric, but have nothing to do with iron. Yeah, so I mentioned how to evaluate it. So it means using the switch charge, and when just transforming from one to the other state of the crystal, you can evaluate the charging current, and so by means of that measure the dielectric state. Yeah, the FRAM, in the FRAM implementation, as I have shown earlier, the capacitor is placed either on the drain or source contact. It depends on the angle of view side of a memory of a selector device, and you can just by evaluating the switching current, you can differentiate which state you have. But you have always to switch when you want to read out the cell. And just by switching, you can see whether the current was low or high, and then differentiate the binary coding of the memory cell. That means that this is causing a destructive readout, so you have always to write back the information when you read out the memory cells, which requires also high endurance capabilities of this memory concept. Yeah, so far it has been already implemented since many years, and the first materials used for the ferroelectric memories were based on perovskite, and they feature exactly that mechanism I have described earlier. Also, polymers are potential for ferroelectric switching, and in our talk we are discussing the hafnium oxide-based ferroelectric materials and also the advantages of such materials. Some of the advantages are listed here next to this page. So it's hafnium oxide is already established in CMOS fabrication, like high-k metal gate technologies, and also it's a quite mature and robust deposition process. It is scalable, so I also come back later to the thickness tuning, and it's already established with standard manufacturing tools. Yeah. So, and for achieving, so hafnium oxide is used in transistors, but it has to be in a special state in order to be ferroelectric. And that means hafnium oxide is not from a basic state, also not in a standard crystal lattice. It is not ferroelectric. But if you do specific treatments like doping or stress, and also special temperature treatments, you get it ferroelectric. And this is the orthorhombic crystal phase, which is having the ferroelectric capabilities. All the others, tetragonal and cubic, are non-ferroelectric and show perfect dielectric behavior. Yeah, and if you achieve that, you can exactly do this kind of state switching just by bending internal the crystal, the internal ion, and then you can switch it and achieve the dipolars inside the materials, which also can be read out in other memory concepts. Yeah, so what is the history? So the ferroelectric in general is not new, as I mentioned. So the material was discovered back in 1921. The first FRAM concept was already shown in a master thesis in 1952. And and then over the years, it was developed more and more based on the perovskite materials. And then there was a certain moment since 2007, the material, the hafnium oxide, was discovered, which to be ferroelectric also, which was also among others a work out of from the Dresden community. And and then over the years, this material was implemented as ferroelectric field effect transistors, and also in other research work implemented as FRAM concept. And the drivers for this ferroelectric hafnium oxide are, as I mentioned, the CMOS compatibility, scalability, the low power features, and also the possibility for application, for applying it in implementing it in various applications. In Dresden, there's also a strong community in Silicon Saxony working on that field, and there's a lot of research among all those partners on this area so that we have also very good community, not only in Dresden but also worldwide with partnerships. Sorry. Yeah, if we look to publications, just numbering the IEEE publications in the recent years for ferroelectric memory, you see, yeah, it has increased since 2015, when it's in the range of 2012 to 15, it was first published, and also especially together with hafnium, the number of publications increased tremendously in the past years. And if you check for neuromorphic capabilities, it even stronger accelerated in the past years. It's quite interesting. So it has a high attention, this material, and yeah, and we are looking forward to much more research activity in future as well on that area. Now let's get back to the technical features. Yeah, in order to motivate the use of ferroelectric hafnium oxide, it's worth to look at the operation window. And if we take, for instance, perovskite materials, which has been used also and also implemented in applications so far, we are in the range of a thickness of 100 nanometers in order to be in a certain reasonable switching area. And if we implement hafnium zirconium oxide, for instance, we are having much higher coercive fields, and that allows us to go to much lower thicknesses with the material. So they can around 10 nanometers switch it already. In other words, it means we can scale the material and apply much thinner stacks, which also paves the path towards 3D integration as well. Yeah, it's just also an example from literature with PZT implemented FRAM concept which have much thicker material thickness. Yeah, so I mentioned it already. So the ferroelectric material can be placed as an FRAM concept, but I just want to teaser also the use as a ferroelectric field effect transistor. So that means the ferroelectric material is directly embedded inside the gate stack, which is another concept and which allows also non-destructive gate out. But this will be another talk which takes more time. Today we will focus on the FRAM. Sorry. So then for investigation of the FRAM concept, we have a Fraunhofer IPMS established a capacitor test platform, which is based on just a cross section on planar or also 3D capacitor devices, which can be investigated, also with smaller dimensions, which are distributed all over the wafer. And so we can investigate, for instance, uniformity effects over the wafer and do process and material optimization. That is just the platform. It has certain test areas and helps to generate results and new findings, which are shown also on the next pages, also on using other platforms like dot samples and so on, depending on what we are doing. Yeah. This platform is open for partners, so also industry partners or scientific partners can use this platform. We can exchange material either pre-processed on our side, then it goes to external partners for material deposition, whatever. Of course, we always need to maintain CMOS fabrication standards, and then it can be looped back to us and we do the final fabrication. Or the other way around, pre-processed material from partners can be processed on our side with our materials, our processes, and go back to the partners. Yeah, so this is something we offer as a platform as from Fraunhofer IPMS. It's capable from on 6-inch, 8-inch, and 12-inch wafers. Yeah, so then some results. It is of course still mandatory to optimize the ferroelectric material, and there are certain factors, as I mentioned earlier, to get it really with a high good ferroelectric performance. There are different aspects. First of all is leakage capability, low leakage currents that we need, and also we also like to maintain a large switching window. And so we evaluated it here. We screened the zirconium content and also this film thickness. And an optimum window or good performance was discovered in the range of 10 nanometer material thickness. Yeah, if you add too high zirconium content, you end up in an anti-ferroelectric-like behavior, which means you don't have a remnant state. It switches back when you bias it to 0. So it's really a matter of optimization. Also, what we'd like to check is, of course, the temperature stability, also the robustness with respect to back-end of line processing, since we'd like to implement the material in the back-end of line environment of fabrications. And for that, we tested different annealing times, and you can also see that it's quite stable and no impact on the leakage. So we could see a good switching windows for several thermal conditions, which is also quite favorable for production. Looking also or benchmarking all the other conditions, you can see that also 10 nanometer offers a low variability and also a stable and robust window for different thermal treatments. And if you go to other thicknesses or temperatures, it's has a stronger variation or dependence on temperature or annealing time. Yeah, that's just in brief some requirements for successful back-end of line integration of the ferroelectric hafnium oxide. Yeah, it's must crystallize in the range of 400 degrees centigrade. That means the material must be doped that way, that only a certain selection of dopants possible to use in order to achieve exactly that. Also, temperature steps and subsequent processing shouldn't harm the material so much, as well as long-term furnace treatments. Yeah. And also the challenge and opportunity which is given here, is that we can integrate the hafnium oxide, the ferroelectric hafnium oxide, into existing technologies, also in existing capacitor modules, which would allow fast time to market, but also low cost adder. So you don't need to implement additional modules or whatever. You can maybe use and bend existing modules. The challenge is, of course, using existing materials and stacks that we achieve also comparable FE performance. Okay, and this is just an example from a project that we've done in the past years together with X-FAB. We first of all optimized material based on dot samples, so we got very high 2PR values, which are quite well. But of course, in real back-end of line conditions and also using existing technologies, is getting a bit lower, but still we can achieve low leakage and considerable switching behavior of the ferroelectric material. So that shows that it is manageable, and of course there's further room for improvement, but in general the implementation is not a high problem. Yeah, so far I've shown you how the FRAM worked, also the integration of ferroelectric hafnium oxide, as well as material and process tuning. And on the next pages I'd like to give you just kind of outlook, future perspective and activities, what could be done as well. First of all, I mentioned already the switch charge, and in order to do scaling, make smaller capacitors, we need to increase the switch charge per area so that we can also scale down the devices even more. And this could be done by implementing the ferroelectric hafnium oxide in the third dimension. And it was already shown that we can already, we can also boost with the area boost. We can also boost the capacitance, and this helps then, to achieve a higher storage density and also a high level of switch charge for the individual capacitor elements. Another interesting topic is field-induced crystallization. This means you can fabricate amorphous capacitors which are not ferroelectric, and then in application or final test or wherever you would like to do it, you can make it ferroelectric just by applying a specific electrical field. So you can do metamorphosis of your device, and it's then also just a matter of optimization of voltages and cycling conditions. And my colleague has proven it in his work the past 2 years that this is possible, and also this effect is clearly visible. So you come from really, let's say, a dielectric behavior to a ferroelectric behavior just by applying a certain voltage or bias level. It's also shown here. If you do specific preconditioning, the material can get to a certain level of switching behavior, and of course you have to avoid then stronger switching conditions in order to transform it stronger and stronger. So this is an interesting topic that we are working on. Another topic is the synaptic device for neuromorphic computing. Due to the interesting subloop switching behavior, which originates from the effect that that we have a kind of the ferroelectric is not just a pure material. It consists of many grains with different angles, and the different angles of the grains, different polarization axes, are also causing then different resulting fields which you require, which you need for the switching. So that means it's not always in plane with the applied electrical field, and this effect helps that we can also switch the material at lower voltages and to certain conditions. And that means for analog switching and also synaptic device operation, we could get a nearly linear switching behavior also with lower voltages, or also the other dimension is applying multiple pulses and using the switching time effect in order to switch the material. Why is it used for? The idea behind that is with neuromorphic computing is that you can place your memory close to the computing elements and also compute in the memory. This is completely different to existing memory approaches, where you have a memory array with periphery and maybe also charge pump and specific high voltage devices. So you have really to decouple it from your core logic devices, which are here, like the processing core. And now with the memories, emerging memories, which are featuring low power capabilities, and also like here, maybe analog switching behavior, you can embed it into the computing element. You don't need this periphery anymore, this high voltage devices, and you can do directly in-memory computing, allowing ultra low power operation at low latency, since you don't need a memory bus like shown here, which is fetching the data from the memory to the computing unit. So that's the end of my presentation. let me briefly summarize what we've seen today. So the hafnium oxide-based ferroelectric material offers good opportunity for integrating in the CMOS technologies. It is scalable, and also there are different knobs for tuning it to specific technology conditions. Also we demonstrated the back-end-of-line integration and also potential for future application use and tuning of the material, like 3D integration, the field-induced crystallization, neuromorphic computing, and also new memory architectures, which is shown here, for instance, placing the capacitor on top of the switching device, so into the gate stack, more or less, but in the back end of line. And here, this allows, this combines the non-destructive readout feature with the FRAM, good FRAM endurance, switching endurance feature. Okay, that's all from my side. I'd like to thank the entire team of Fraunhofer IPMS, especially also Peter, for preparing and organizing this talk. Then also to our funding and project partners, many thanks for all these valuable discussions on this topic, and to the entire CNT team and my colleagues. So now I'm back at the beginning, and I'd like now to point at MRAM and Lucas.
Thank you very much, Konrad, for this interesting talk. If you have any question for this or the next topic, or you can ask your questions here in your the GoToWebinar panel, so please don't hesitate. So I would like to continue with our Spintronics team at CNT, where I am also located in the business unit for Center Nano-Electronic Technologies. We have been only established a little bit more than 2 years ago. We are very dedicated and enthusiastic in this field. Mike Wagner-Retz is here the group lead, and here you can see all the colleagues who are supporting or supported with content, and also are working on this topic, and we building up this exciting technology. So we are here in spin-based devices. So we are using the spin of electrons for creating non-transitional components beyond what is possible in only a CMOS. So we are using here the spin up and spin down of the electrons itself, and not only the charge. So it's building with intrinsic magnetic moment. We use it as a building block for logic and memory devices. Here, you know the use of the spin at the hard disks in the last decades, for sure. We hear that Spintronics in the micro or nanoelectronics, we are using tunnel magneto resistance for changing resistance states, and so to induce a switching behavior. Here in this case is a SOT device, for example. This is the most important thing is here the magnetic tunnel junction. We have a fixed layer and a free layer and a tunnel barrier in between. And if we have here a parallel spin, then we have a good resistance and a good conductivity through the tunnel barrier. If you have an anti-parallel spin, we have a bad conductivity and a high resistance, and this is the basis of this kind of memory device or this kind of sensor device. So in here you see a picture from H-probe, where just by applying the magnetic field you can induce the high and low resistance state, and have also hysteresis, where you have enough space for this switching. In our group, we are coping with several approaches. Of course, we're now integrated or established process, even in products, the spin transfer torque, where we are working here at our site in the back end of line CMOS. We are working also in the spin orbit torque field, which is potentially faster than SCT MRAM, but it's more in the R&D phase. We are also working here in project with Max Planck in Halle with racetrack memory. So this is next generation MRAM technology. Here we have a potential for low power and high density applications, and for sure also materials for beyond CMOS. So with a high charge spin conversion, we can have a high spin Hall engine and use also this for new devices. So, but what are the challenges here? Because in the last decades, we already introduced a lot of new, a lot of materials in the semiconductor environment, and we have an increasingly demanding semiconductor industry and customers. And so since the 80s to the last decade, we have 6 times more materials from a periodic table, and now with such novel technologies, such we have here even more materials and even more which was considered in the past as exotic materials. Here you have a periodic system, and we look at every metal that is possible and what if it's already established, what we want and what we really don't want. So we look at literature at our partner sites, and also from experience, what would be the next material. We have here protocols for established one, like for back end of line and front end of line, here in green, or memory devices, and the blue one, what is interesting in our case, mostly in MRAM. So we have like ruthenium, iron, magnesium, and so on. And this has to be filled into a contamination protocol. So therefore it's a lot of effort, and we have a lot of effort in metal tracing analytics, and what is the interaction with metals with other technologies we already have. For this materials we want to use, we have a new PVD sputter cluster tool from Applied Material. This will be here the working horse for spintronic materials. We have here also other analytic methods like a magnetic prober, like from H-probe, current in-plane tunneling measurement tool by KLR, where I come later to this. Of course, also conventional metrology tools, X-ray reflectometry, X-ray diffraction tools, like here inline, electron microscopes like with TM, like here from FEI, or optical measurements tool like with ellipsometer from Wulem. So this is all for material deposition and material characterization. This is not for device building. These are much more tools available. So back to the PVD equipment, what we have here. We have 2 Applied Materials Endura mainframes and 3 different fields where we are working with them. We have a back end of line, so the interconnect area. We have a front end of line, or high K field. This is an own protocol zone as well as a BOL, and the new material from MRAM we have here in this CL5 code protocol zone, and this has all to be coped with. I will not talk about the backend of line. This is another tool, which I will talk about Endura, where we have this 2 protocol zone at once. And now more in detail, I will talk only to the materials we can deposit in an N-metal, or let's say how we analyze them, how we characterize them. The Endura Cloud tool chambers and with the mainframe, with Endura mainframe was only released in 2019. So at the same time, our group was founded. And this is our tool setup. We had here for each chamber, we had 5 targets, 5 materials that can be used. The tool is developed for emerging memories, mostly for MRAM, FRAM, FRAM, and much more. So it can, of course, also deposit electrodes and metallization. But in our case, we use for memory and sensor stacks. With the MRAM chambers, we can deposit more than 10 metals. It's here on the so-called transfer part of a tool. Here 16 targets can be mounted at once. Mostly you use more than 10 materials, 10 metals that can be used. It's a typical MRAM metals like cobalt iron bore, cobalt platinum, cobalt tantalum, and much more. And we have also one part, but it's divided from protocol zone with dual handler due to the dual handler mode with FRAM chamber, where we can deposit the materials which Konrad mentioned for hafnium oxide, hafnium zirconium oxide for this application. And here we can do also co-sputtering, RF sputtering DC and pulse DC options. So how these chambers look like, we have here 5 different targets. We have certain power range and variety of gases and gas flows that can be adjusted for process development. The chuck is where the wafer is rotating. The pressure range is between 0.2 and 2 millitorr. So during the glow discharge and in idle mode, we have a pressure of mid 10 to -9 torr. So during deposition, it looks like this, that the wafer, this is a picture from Upper Materials, the wafer is rotating and the targets are selected by this rotating hole shield. So it can be deposited without breaking the chamber vacuum or without moving out of the chamber itself. And then you can deposit without breaking the whole vacuum, a substrate, a seed, a synthetic antiferromagnet, the buffer layer, reference layer, tunnel barrier, and free layer, and the top electrode. So we can deposit with a stem stack with more than 40 layers in less than 30 nanometers. And the challenge here is to design the complex stack and fulfill the high demands on metrology and analytics. So how we measure a layer with less or than 1 nanometer till a few nanometer? Conventionally, we have standalone metrology tools. We avoid oxidization by having a cap layer or in inert material, or we live with it by calculating them. And then we extrapolate this for nominal film thicknesses. So we have to check the linearity, but the linearity for several deposition times is the linearity is guaranteed, and we have to be aware of our substrates for sure. Normally we use X-ray reflectometry, spectroscopic ellipsometry, and resistance mapping, for example. So each of them has their own advantages and disadvantages. So you have for reflectometry takes long to measure, but you have a very high stack accuracy. For ellipsometry, you can make nice maps. It's quite fast, and but it's dependent on the model you use. So you have to develop for each quite elaborated model. Resistance measurement is quite fast. You can also make maps, but it can measure only unit films. And of course, it's the resistivity is dependent on the thickness in these ranges. But sometimes it's exactly what you want to know. And for sure, other methods for troubleshooting in references like electron microscope or photon X-ray photonic spectroscopy is also possible. So as you've seen, normally for uniformity's sake, the wafer is rotating. We can stop this, so we can vary one layer. We can within the free layer, we can vary by just not rotating and have here a slope of thickness of a certain layer, and have a higher thickness and a lower thickness, for example. And this can be also seen in the current in-plane tunneling measurement for the tunnel magnetoresistance in a full stack, and also the magnetic behavior in a VMR, in a vibrating sample magnetometer is also possible to see if you have samples from thicker layer and lower single layer within the stack. Of course, the wafer map is ellipsometry quite good. We have here used a variable angle spectroscopic ellipsometry screening. This is suitable not only for uniformity check, but also to obtain better optical parameters out of each material, and then to have a thickness estimation. Here are 5 typical materials, as like I told before, and the non-uniformity is mostly superior and can be cross-checked by X-ray reflectometry, which is for sure not that model dependent like ellipsometer. And here's an example of a platinum deposition of 3 different thicknesses to see if the linearity is very good, and therefore we extrapolate it to even to lower thicknesses to have nominal values. And this is also true for nearly every material we used. That is quite usable, and you can work with the extrapolation. Of course, also with electron microscope like high resolution TEM, we can produce special stacks, very big stacks, without breaking the vacuum. In this case, between every single metal layer and also between thickness splits between metals, we have isolating material in between to enhance the contrast for the TEM measurement, and therefore we can have a good reference and to see for the thickness by only one TEM shot, because as most of you know, is quite high effort, and due to the in situ deposition, we have no vacuum break. The alternative would be to deposit only one layer, and with CAP and have one analysis for every material. So for STEM 8HDF, you can also see a different contrast. Also, the isolation material can be seen, and EDX depth profile, you can see, for example, alternating the isolating material in between the metals. Of course, for characterization of a material, the resistance is quite very important, and is also a field, and this can be done by the same systematic. So you see the thicknesses, different thicknesses. You have a top layer. You have you determine a resistivity model by this. You can extrapolate, and you can see what would be the thickness. Interpolate or extrapolate. What's the resistance here? And in this case, we also have to calculate the platinum cap and calculate this out with a parallel circuit consideration. But last but not least, I will also talk about the other film thickness measurements, which are quite important for this memory stack development. We have not only standalone tool, but an integrated approach. There's 3 possibilities as in a front interface test station outside of a vacuum. This is not feasible due to the vacuum breaks, so you can already use a standalone tool. Then in the mainframe outside of the chambers, you have an in vacuum metrology position. This is mostly sufficient for process control and development, and for sure for in situ high maintenance, in situ process chamber setup would be nice, but has a high effort, and but you would have a real-time process monitoring. We have here an onboard metrology solution for sub-nanometer precision measurement in the mainframe. So it's a good fingerprinting method since referencing is crucial, but if it's like good calibrated, you have a very good sub-nanometer accuracy. And PVD, as you've seen, is known for aclinia, so you can see very slight changes here. The principle is that you measure the change in intensity of a light reflection on the surface of the function of wavelengths. And of course, what is very important here also is the silicon, bare silicon calibration, that you see that you have a stable signal. So the challenge you cope here with is to measure very fast and very reliable in these ranges which are desired. And it's a quite fast method. You have only a few points, but it is less than 30 seconds. So you have a true fill measurement. You can always make an altimeter outside of a tool. You have a baseline comparison. You have a frequent monitoring. And you have it's anyway in the process control roadmap within. For troubleshoot and references, you can anyway use the other methods. So you can measure the stack at the substrate at the start, after the first layer, or for one layers, in between, so before and after the tunnel barrier, or at the end of a whole stack. And of course, we checked the linearity. It's consistent results from models if the model is for metals, if a model is elaborated. It's good for in vacuum process verification. And it's a good process control for volume manufacturing, fast measurement, high repeatability. It's a good tool. So at the as I said at the beginning, two tools which are very dedicated to MRAM. I would like to mention. We have CIPT, the current in-plane tunneling tool, where we measure the tunnel magnetoresistance of a magnetic state on a bare silicon wafer, which on a bare wafer, not silicon wafer, pure silicon wafer. But we have a 4-point probe resistant measurement under a magnetic field, and here's a special probe set that is necessary, and you can even map this, and it's also by major IDMs checked if you have the same result like they have, if, and the measurement takes approximately 1 hour, and it's quite, the measurement is then quite automatically, and also simple errors is for sure possible. The other metrology tool we have here for that is dedicated for MRAM is the H probe. It's characterization for MRAM devices for characterization. Also 300 mm wafer capable, and you can of course automatic manual wafer on coupon level. You will test with tunnel magnetoresistance, the TMR, right error rates, and endurance, and it's for different MRAM approaches possible. So we have here magnetic field. You can generate a magnetic field up to 7,000 Ørsted, as well as have pulse signal and use a stage that can be heated or cooled. So we have a high variety of materials possible within the cluster system, and in vacuum metrology we have sub-nanometer accuracy possible. Have a high we cope with a high requirement on cap, on substrate, and so on. So it's a well-established metrology flow. We can handling within a CMOS environment, and it's still an ongoing challenge for producing devices here. You have, and we see that cross-reference between analytics is crucial. This is accessible. This materials and other tools are accessible through the Access Plus project. So together with access providers like INL, Leti, Tyndall, IMEC, and some more Fraunhofer institutes, we access transnational. We provide transnational access. There's a knowledge hub, there's a community network. So please visit our site. We see here in the top, and this is part of our showroom. So you have we have different topics, different platforms where you can see if a material or if a topic is of your interest, and so it would look like here if it's a tool request or material request or processing request, that shows where it's available, what you can do with this, or if it's a clean room or not clean room, and so on. It's mostly fitted for 300 millimeter, but still we here very flexible. So I thank you very much for your audience. If we will just look if you have some questions, and yeah, thank you very much. So one question was already answered. The access to these facilities is here through the SN Plus website. That's also with here funding. The great thing about this is that it is perfect for feasibility studies or tests, or since it is really the access is free of charge. For sure, it is the access is for sure limited for the project for a certain topic, and so it is to establish a European-wide network, and it also is possible for having here to get known to each other, and to use this as also help engineers or PhD students to get in contact with high performance materials, high performance technologies. So something else. I think one question was to Konrad. This second order phase transition. I don't know exactly about this slide was this. Do you know how to answer?
It points in the direction of I guess slide. Thank you.
Slide 10 to 11. Good. Slide 10. Yeah.
10 to 11. Okay, then I will check the slide. Yes, so that means it's directing in at the ferroelectric switching property, and whether this transition is second or first order. Yeah, that is hard to say. I discussed it already also with my colleague. So this, if we do it at the Curie temperature, we can say it's first order. But below that, it could be, it's hard to describe and hard to answer this question. So since it's not a stable condition.
Great. So we just have, I think, 4 p.m. So just in time. Of course, if you have more questions, please don't hesitate to contact us directly by email, by phone, by our social media platform, wherever it's suitable for you. And thank you very much for your audience, and see you next time.
Also from my side, many thanks for your attention. Thank you, Lucas.
Thank you, Konrad.